Power. Power is the work done per unit time or energy dissipated or transferred per unit time. Let me explain this with an example. Imagine, or for example, the person 1 applies force on this box and moves from point A to point B. I'm repeating, this person 1 applies force on this box and moves from point A to point B and takes 13 minutes. And the person 2 applies force on this same box and moves from point A to point B, but he takes 19 minutes. Both did the work. Work done is equal to force and displacement. Force is applied on this box and distance is covered from point A to B. Force is applied and distance is covered. Means work is done. This person 1 did work in 13 minutes, but person 2 did work in 19 minutes. So person 1 has more power because it took less time. Person 1 has more power because he did work in less time. Work with respect to time is called power. Work done per unit time is called power. Hope you got the point. Work done per unit time is called power. Take another example. A water pump A and a water pump B. This example is from electrical power sources. DC electrical power source a battery is. A water pump A fills this water tank on the first floor in 15 minutes. And the water pump B fills this same tank at the same height but in 25 minutes. Same tank, so water pump A has more power because it did the work in less time. It took less time. So it's an example from electrical power sources. When we close the circuit or turn on the water pump, we close the circuit, these electrons will flow through this water pump and the armature of water pump will start to rotate. So it's an electrical power, DC electrical power a battery is. So power is work with respect to time. So we can replace work with an energy because we know that sometimes work is converted into potential energy, sometimes work is converted into kinetic energy, sometimes work is converted into electrical energy, sometimes work is converted into heat energy. For example, when force is applied on this duster, a work is done. But this work is stored as a potential energy in this duster. Work is stored as a potential energy in this duster. Another example, when I rub my hands together, work is done because force is applied from this point to this. Force is applied, then distance is covered, means work is done. And this work is converted into heat energy and sound energy. Your hands will be warm. So work is converted into heat energy as well as in sound energy. So here work is converted into potential energy, here work is converted into heat energy and sound energy. So we can replace work with energy. Potential energy is measured in joule, kinetic energy is measured in joule, heat energy is measured in joule, sound energy is measured in joule, work is measured in joule. So we can replace work with energy. Energy dissipated or transferred per unit time is called power. Energy consumed, dissipated or transferred per unit time is called power. It's another example of definition of power. Now, as we know that work done per unit charge gives the electric potential difference. Positive charge plate, negative charge plate, when work is done on this charge, gets electric field from this point A to point B. Work done on charge gives the potential difference from between point A and B. Work done per unit charge gives the electric potential difference. Q will be multiplied with V. So W is equal to QV. So by putting the value of W over here, the equation becomes P is equal to QV over T. P and T both are same as it is, but W is replaced with QV. Now, Q over T, flow of charge per unit time is called current. Rate of flow of charge is called current. So, power will become, this equation will become P is equal to VI, voltage and current. This expression provides another definition of power, which is product of voltage and current. Another definition of power, which is product of voltage and current. As we know that according to Ohm's law, V is equal to IR. By putting the value of V, this equation becomes this I as it is, and this equation becomes P is equal to I square R. Now, the R will be divided under the V, then I is equal to V over R. By putting the value of this I, this equation becomes, this R will cancel with this square and P is equal to V square over R. This expression gives power as a function of current and resistance. Power as a function of current and resistance. And this equation gives power as a function of voltage and resistance. Power as a function of voltage and resistance. Now, the units of power. The SI unit of power is watt. The SI unit of power is watt. Watt. The SI unit of power is watt. Equal to the SI unit of work is joule, and the SI unit of time is second. So watt is equal to joule per second, or the SI unit of power is watt equal to voltage is measured in volt and the current is measured in ampere. Another equation for watt is volt ampere. Here watt is equal to joule per second. Here watt is equal to volt ampere. So that's the unit of power is watt, which is equal to joule per second or volt ampere. Now the definition of watt. If 1 joule work is done in 1 second, then the power will be 1 watt. If 1 joule work is done in 1 second, then the power will be 1 watt. Another definition, replace work with energy and done with dissipation. If 1 joule of energy is dissipated, 1 joule of energy is dissipated in 1 second, then the power will be 1 watt. 1 joule of energy is dissipated in this resistance, in this load resistance, then the power will be 1 watt. This definition is in terms of electrical power, and this definition is in terms of mechanical power. Now, types of power. Mechanical power, this is an example of mechanical power, whereas this is an example of electrical power. Mechanical power, electrical power. Electrical power has further two types. AC power, the power of AC generator or AC current. DC power, the power of DC current or battery, etc. Now, don't draw this diagram in your exams. It's only for the understanding of basic concept. Draw this diagram instead. It's a symbolic version. These two smaller and bigger lines represent the battery. This zigzag smaller line portion represents the internal resistance of this battery. And this bigger zigzag line represents the load resistance or load. Energy dissipation in circuits. Energy dissipation means energy lost as heat when current flows through the resistor. For example, when current flows through this bulb, it becomes hotter because some of electrical energy is lost as heat. You can touch it. You can check by touching it, it will be hotter. Same phenomena is happening in the fan. When current flows through this electrical fan, it becomes hotter. Some of electrical energy is lost as heat. This loss of energy is known as energy dissipation. Energy dissipation, when current flows through a resistor, energy is lost as heat. This is called energy dissipation. Mathematically, as we know that power is equal to work done per unit time or energy dissipated per unit time. When we move T to the other side, it will be multiplied by P. Then the equation will become E is equal to PT. Now, we know that power is equal to the product of voltage and current. So, by replacing P with VI, T will remain the same. The new equation becomes E is equal to VIT. So, according to Ohm's law, V is equal to IR. Replacing V with IR, this I and T remain the same. This I and T will remain the same. Only V is replaced with IR. Now, two I's becomes I square. This R and T remain the same. So, this is the equation of energy dissipation in terms of current, resistance and time. Equation of energy dissipation equation in terms of current, resistance and time. Current, resistance and time. Now, as we know that V is equal to IR according to Ohm's law, when we move R to the other side, it will be divided by V. So, by putting the value of I over here, the new equation becomes is equal to V over R square RT. Now, after the cancellation of this R, the equation left is equal to V square T over R. Now, this is another equation of energy dissipation in terms of voltage, resistance and time. This equation provides the energy dissipation as a function of voltage, resistance and time. Voltage, resistance and time. Now, it's energy dissipation, now power dissipation in circuit. They both are almost same. Power dissipation, power lost in the resistor, both internal resistors of source as well as in load resistors, is known as power dissipation. For example, PEMF is the total power provided by this source. This is a battery. This is a symbolic version of the diagram. PEMF, total power supplied by the source to a unit charge to move through the circuit, is PEMF. PR, power dissipated or power lost in load resistors, or PR is the power dissipated or power lost in the internal resistors of the source. As we know that power is equal to product of voltage and current, and we can also write P is equal to EMF multiplied by I, because EMF and terminal voltage both are almost equal. There is a slightly difference between EMF. EMF is the total energy and terminal voltage is the energy left at the terminals. EMF is the total energy provided to the charge and V is the energy left at the terminals of the battery. They both are almost equal. So we can write P is equal to VI or P is equal to EMF multiplied by I. So it's VI now. This power is written in terms of resistance because its energy loss in resistance R. So it is written in terms of resistance. This is also written in terms of resistance because it is energy lost or energy dissipated in internal resistance of the source. That's why they both are written in the form of resistances, and this is energy provided, not a lost. Energy provided by the source, so it is written in terms of, and this energy is provided in terms of voltage and current. That's why this equation is written in terms of voltage and current, or EMF or current. This is the mathematical equation for power output. For power output, for example, for maximum power output, if 32 is divided by 60, the result will be 2. If 32 is divided by 2, the result will be 16. So, smaller the denominator results in greater value. Greater denominator results in smaller value. So, for maximum power output, the denominator should be smaller. Denominator should be smaller, the power or resultant value will be greater. So, for maximum power output, denominator should be smaller. The denominator should be smaller if the load resistance, this one, and the internal resistance, smaller, this one, both are equal. If capital R and small r are equal, then denominator will become smaller and the power will be, denominator will become smaller and the power will be to its maximum value. So by replacing this small r with the capital R, this small r is replaced with the capital R and this small r is also replaced with the capital R. After the cancellation or simplification, the equation left is EMF square over 4R. Now this denominator is smaller as compared to this one. So the power reached to its maximum value. So for maximum value, for maximum power output, the load resistance should be equal to the internal resistance. Load resistance, this one should be equal to the internal resistance, this one. Then the denominator will be smaller and power will reach to its maximum value. Hope you got the point.